Welcome to everyone. It's my pleasure to kick off this event. You can see the first slide already streamed. The workshop is Parallel Computing with MATLAB Part 2. Many of you that I see from the attendees list have been already with us for the event number 1, that was Parallel Computing with MATLAB Part 1. That has been held in the beginning of June with our colleagues from MathWorks'ten Raymond Norris, Jonathan Murray, and also Sebastian Gross. This is the part 2. The part 2 it will be about how to scale parallel computing with MATLAB to the nationwide HPC center of TÜBİTAK Truba that you see with the main logo at the center of this slide. Therefore, if your goal is scaling your computational effort to the national-wide cluster to be the Truba, or if you want to run batch jobs, parallel computation, and provide an understanding of the caveats in running in this cluster, you are in the right place. Welcome from my side. I'm Marco Rossi, Customer Success Engineer from MathWorks, dedicated Turkish academia. Together with me, the speakers of today's talk is Raymond Norris, Application Engineer at MathWorks in the Parallel Computing team, talking to you from Natick, USA. And in the chat, there will be different persons to support you. There is me, Alex Tarchini from MathWorks, Jonathan Murray from MathWorks, and also Sylvain Schwaller from FICES. In today's talks, we will have also two academics from the University of Bilkent, Dr. Ghaith Makey and Dr. Michaël Barbier, two researchers in the Simply Complex Lab at Bilkent University. Let me welcome also them. Thank you for your participation. Also, a special thanks also to Bilkent Truba for the collaboration that we have put it in place, and a big thank you also to FICES, MathWorks official reseller in Turkey, for the help in the organization of this event. With that, welcome also to the audience, to everyone. I will be very happy now to give the stage to Raymond Norris, that will start the talk. Raymond, welcome, and thank you so much for being here.
Well, great. Thanks, Marco. I appreciate the introduction, and welcome everyone this afternoon to our second part of Parallel Computing with MATLAB. What I'd like to do is sort of set the stage of what we're going to be doing today. For those who were able to attend our Part 1 workshop last month, you know that we spent a fair amount of time focusing on the MATLAB parallel language. So that is that we were learning what a parallel for loop is, what a parallel pool is, SPMD, GPU arrays, and so forth. So our focus really was, how do we run our code locally on our host machine? How do we debug, troubleshoot, prototype our parallel application, etc. But at some point, you'll need to perhaps extend those resources to other compute, and that's really where we're going to be focusing today. So our focus is going to be understanding, once we've parallelized our code locally on our host machine, what's the process in order to be able to scale to an HPC cluster such as Truba, which is what our focus is on today. So where last month we were talking about the Parallel Computing Toolbox, today all the focus is going to be on using the MATLAB Parallel Server. As Marco mentioned, we strongly encourage folks to actively participate in today, and when you do, we ask that you at least post to the host, presenter, and panelists. I will do the best I can to monitor the chat, but really we have an excellent team that's monitoring the chat, and they'll be able to answer questions as I'm talking. However, I think your questions are questions that everyone has, so if you're encouraged to, or you're comfortable, if you could submit it to all attendees, so that way we can all see the questions, and when the staff are answering the questions, we'll all get to see those answers and so forth. So. Okay, so Before we get started, though, what I'd like to do is bring in our guest speakers today. They will be talking about how they went about actually using the MATLAB parallel server to scaling their code. And they'll talk about a little of their study. They'll talk about how they did go about running things locally and as well as running things on the Truba cluster. So with that, Alex, I'd like if you could make presenters our guest speakers this afternoon to have them walk us through their findings.
And Ghaith, you're now a presenter and can share your screen.
Yes, thank you. So you can see my screen now, right?
Yes, we can.
Thank you, Raymond. Thank you, Alex, Marco, and everyone. I'm Ghaith Makey from Assembly Complex Lab, which is located in Bilkent University, Una, and led by Siren Eldar. In this group, we are interested in systems operating under far from equilibrium conditions, such as high nonlinearity, strong stochasticity, and the presence of intrinsic positive and negative feedback mechanisms. One of the topics that interests us is the universality, namely that multiple unrelated systems, which can be physical, mathematical, or social, who share similar behavior in some aspects. So that sharing is called universality, and one example of that is the mysterious Tracy-Widom distribution, which is similar to Gaussian distribution, but with this positive or negative sequence. So this distribution shows up in fluctuations among those unrelated systems, and is expected to show up in some weird places like in the distribution of photoreceptors in avian retinas. For us, we want really to study and investigate the presence of that distribution. So for that, we constructed a flexible experimental setup at which we have a microscope slide. There is water, and within the water there are swimming particles or organisms. And we shine ultrafast laser. The laser hits the sample and forms some flows. The flows attract the particles and aggregation form and interact in feedback mechanism with the flows themselves. So we have aggregation with the growing. And we studied the temporal fluctuations of the average radius growth, and we found a Tracy-Widom distribution within. And that was interesting because it was the first reporting of temporal Tracy-Widom distribution, which was expected to show up in the roughness of the boundary of the aggregation, not in the growth in time itself. That was published in Nature Physics, and now we are interested in understanding why we got temporal Tracy-Widom distribution within mathematical framework. So we go to HPC equation, which is used to, widely to simulate or to understand the growth of nonlinear aggregation. So we have particles going down, and we have growth going up, and roughness also increase in time. So the traditional HPC equation has term for spatial nonlinearity, diffusion, and randomness, and all those are along the interface. And long story short, we decided to add two other terms which show temporal nonlinearity, so along time, and temporal diffusion. We want to take this equation and see if it can really explain the results that we get in the experiment. The point here is that this equation is a partial differential equation with multiple terms, and we have multiple constants, which large spectrum of values, which is the balance between different terms. The study is statistical, so needless to say that we need a huge amount of points along the interface, many time steps, and for that we really need the help of Truba parallel server, and it came to help, and that's what my colleague Michael will explain now. So Michael, the floor is yours.
Thank you, Ray. So as Ray said, we have a lot of data points to compute, and this code is perfectly parallelizable. So, first, for that reason, we first parallelized our code, which is a MATLAB script, to run on our own computers in parallel. And basically, for that, we just switched from a for loop to a par for loop. Then, to further scale up this workflow, we wanted to implement this on the Truba cluster. So for that, we basically required the license, and we actually had a pretty smooth, let's say, transfer from our own computers to executing in parallel on the Truba cluster, as most of the things are similar. The only thing, and which you probably already know, is that the job queue, instead of instantaneous execution, you have a job queue, you submit your job, and you don't look further to it. But then in our hands, let's say, I just want to give a quick heads up. We really had to optimize the number of processes versus the number of threads. It might be that the MATLAB experts will mention this today as well. Now, and then I just want to give you the experiments, our experience on the performance on the slide on the right. And if we zoom in on that part, then these are, here we did some tests. So we have 3 different tasks that we tested, so 3 different scripts, and we tested them on basically 4 computers. So we have 2 laptops, 1 master student's laptop and 1 PhD student's laptop of our lab. Then we have a workstation in our lab, which is a new high-end workstation, and then we have the Truba cluster. And we executed all the same test scripts, which ran only for a short time. The details of the computers you can see here on the right, and on the left, I showed you on the graph the different timings. And then let's watch, let's look at laptop in blue and basically blue in the red bar. Then you see that for task 1 and 2, the laptops are definitely slower than the Truba cluster, which is denoted in purple. And we definitely got a speed up there, and this definitely scaled up. Now, I just want to mention, so we also added here a workstation, which is in our lab. And so it kind of gives about the same results in timings for the first two tasks. The fact that it gives the same time is kind of expected. We actually asked for the same amount of workers in the same worker configuration on those 2 computers. We just wanted to see what our experience of this workstation, which is not in a queuing system, let's say, versus on the cluster, and this should give about the same result, and it does. The only thing is, of course, the cluster is scalable. So if we want to, let's say, execute more scripts on the cluster, we can just ask for more cores, while our workstation, it's a single workstation. If we want to execute more codes, then we need to buy another workstation, of course. Then for the last task, I also just, we executed this hyperuniformity analysis task. And at first it was a bit odd, so the Truba cluster was taking actually longer, but then we looked into this task and we saw that like 80% of the work was visualization. So 80% of the time, the computer was doing basically visualization tasks, which are not parallelizable. And because this is sequential, it doesn't really matter how many cores you allow this code to use, it will just mostly use one core. So most of the time it is not, nothing is being sped up, and that you see in this graph. So if you have a code which is not parallelizable, then you need to either execute it on your own computer, or you need to split the parts which are sequential and ones which are parallelizable. And then I want to wrap up just to say that we are currently also testing other codes on the Truba cluster other than the Tracy Widom scripts, and we are seeing which ones we can upscale or increase the performance of by using the Truba cluster, and also some codes we actually think that they would be very good, also highly parallelizable codes, which would be good to test and maybe use the Truba cluster also within our group in future. And with that, I'd like to thank you all for listening, and we are open to any questions. Thank you.
Great, thank you very much, gentlemen. I really appreciate it. As Marco mentioned, if anyone does have any questions, please feel free to post them in the chat, and our guest speakers will certainly be keeping an eye on that, and we'll be happy to answer any follow-on questions. I do want to come back to actually to their slide at the very end. I think there was some really good observations that were made as far as timing and so forth, so I'm going to pull that last slide in towards the end. But I want to focus on one comment that Michael had just mentioned that I think is worth mentioning now, and that is that there's a lot to consider when you're parallelizing your code. And I thought his observation of seeing what is that you can truly parallelize is very important when it comes to timing and setting expectations. So I'll make a very simple example. Imagine that the code that I want to speed up takes 10 hours. And maybe there's 2 hours of some data cleansing and importing of data and so forth that can't be serialized. And then there's maybe another 2 or 3 hours of post-processing, whether it's generating a report, plotting, et cetera, that also couldn't be parallelized. But it's that sort of middle chunk of 5 hours that's the heavy compute. So we could throw 1,000 computers at it, and the best that we can do is get a 2x speed improvement, right? If we go from 10 hours, let's say we can drive that 5-hour compute down to 0, we're still left with 5 hours of pre and post processing, graphics, et cetera. So we can only get a 2x speed improvement, right? So really what we're focusing on not is timing everything, but timing that which can actually be parallelized. And in part one, some of the things that we talked about are the tools that you have at your disposal, right? So first and foremost is that you want to use the MATLAB profiler, right? And so this you can find in your, let me bring, when I bring MATLAB up, I'll show you where we can find it. But the profiler will instrument your code to identify those areas of your code that are running faster or slower than other parts. The second is using the code analyzer to help identify where you can make improvements to those pieces of code that are running slow. So for instance, vectorization, pre-allocation, et cetera. Once you've identified what's taking long, why it's taking long, then you can start figuring out what things you can do, and whether it's using a parallel for loop locally or running things on Truba, et cetera. That's really where we're going to be focusing, of course, today. So thanks again, gentlemen. I appreciate it. Great observations. And again, I'm going to circle back to some of the points in the chart talking about the workstation versus Truba towards the end of the presentation. So today we're going to go until close to the 4 o'clock hour. This is unlike part one, which is more of a hands-on workshop. This is more of a lecture format, so it will be very much of a do as I do presentation. So I would encourage you to follow along in those places where it makes sense to do the same things that I'm doing, and I'll show you where that is. But there are other parts where I'll simply be talking through and talking about some key points and whatnot. So the first thing that I want to say is that today's lecture is really all about process and not performance. And what I mean by that is that, of course, understandably, I simply don't have time to run a 45-minute example and show that we can run it in 5 minutes or 10 minutes and so forth. Instead, what I want to walk you through is the process of being able to have your MATLAB desktop, or rather MATLAB running on your desktop system, being able to submit jobs to the cluster, right? So these are going to be very contrived examples, but it's talking more about the workflow of how we're going to submit jobs to the cluster, get results back, be able to determine if there are issues, how do we troubleshoot, if you were going to put in a help ticket, how do you go about, what information might you need to do that, and then in the end we'll talk about even licensing and next steps and so forth. So, all right, the presentation is being recorded, and we'll also have these slides posted on the site that you'll have access to momentarily. The link that I've provided here is a work in progress. We'll be updating this user guide. However, I've included the user guide in the support package, which we'll work with in a moment. The last thing is, hopefully everyone's aware that it's in order to actively participate in the workshop today, that you need to have both MATLAB and the Parallel Computing Toolbox, and specifically, you need R2021B. And the reason is because we've installed already all the software that you need on the cluster. However, it's version specific to R2021B. So the first thing that I would say is that if you don't currently have MATLAB, or you do but it's not 21B, please continue to stay on and watch what we're doing. Again, there'll be a couple of times where we submit jobs to the cluster, but I think you'll learn a great deal, even if you're not, even if you don't have MATLAB or R2021B installed on today. The second is that if you have an older version or a newer version rather, so maybe you're running 22A, et cetera, please let us know, specifically let the TÜBİTAK folks know, so that perhaps we can get a newer version installed on the cluster as well. Everything that we're talking about today is backward compatible all the way to R2017A. We just need to know what versions that you're running and what versions you'd like to see on the cluster, and perhaps we can make some adjustments for that. And the last thing is that it requires obviously having an account on Truba. If anyone does not have an account on Truba, please post something in the chat. Marco and Alex, I'm going to put you on the spot momentarily. I believe you received the email from the TÜBİTAK folks yesterday, and so if you could look at that, and if there happen to be some folks who don't have an account on Truba, please make use of that list. It is a unique list, and what I mean by that is that only one person can use it at a time for technical reasons. So, okay, so maybe if anyone could just throw in the chat if they don't have MATLAB installed right now, or if they don't have 21B, version 21B specifically with the Parallel Computing Toolbox, or if you don't have a Truba account, if you could please post that in the chat, and then we'll try to adjust as we can. But with that said, I'd like to get started. Okay, so I think it's important to sort of understand the basic workflow of how we're going to get jobs running from your MATLAB client to the cluster, right? So everything that we're going to focus on today is using what I'm going to refer to as remote submission. That is, from your university, you have already installed and are using MATLAB and the Parallel Computing Toolbox, right? So your host machine, whether that's Windows, Linux, or Mac, is going to be running MATLAB. On the cluster side is where we've installed the MATLAB Parallel server. So that's already taken care of for you. And really, I'd like folks to think of the MATLAB Parallel server as really being almost identical to MATLAB, except for it simply doesn't run a graphical interface, right? So we're going to be running these MATLAB processes that we call workers in order to scale your code across multiple cores, multiple nodes, et cetera. And the way that we're going to do that is introducing the batch command. Now, for those who have already written parallel code, whether it's you've already been writing it for a while or it was when you learned about it last month, really our focus was using parpool. Parpool allows you to run an interactive session versus batch is more of a non-interactive session. And I'm going to spend a little more time in another slide or two to talk about the differences. But the primary difference is that with the batch command, it allows us to automatically generate, in this case, a Slurm job script on our local machine. We're going to copy it over to the cluster, and then we're going to submit that job on your behalf. And so when you look at the way that this works, you'll start to see that there are certain configurations or certain parameters that we can specify for Slurm through the MATLAB API. Right? And again, that's through the batch command. Now, the nice thing about the batch command is that it's asynchronous. That means that it doesn't block MATLAB from doing other things like calling other functions, quitting MATLAB, and so forth. But certainly one of the things that it could also do is just submit another batch job, right? So while your first job is being run on a cluster, you could launch another MATLAB parallel job onto the cluster as well. And I think this starts to become where, we sort of think of HPC as high productivity computing, where you're going to have the ability to seamlessly, from your MATLAB client, be able to communicate to the cluster, all staying within the MATLAB environment. Now, some of you may already be familiar with Truba or your own HPC cluster at your university. You may be familiar with schedulers like Slurm or PBS and so forth. What we're going to show you today is the ability that you can do all of this from within the MATLAB environment and not need to necessarily connect to the cluster to get the status of the job and so forth. So we'll show you how all of that works in a moment. Okay, for the MathWorks folks, I'm not really going to be paying much attention to the chat, so please interrupt me if there's something that I need to address. All right, so with that said, let's talk about this notion of profiles. So you've been using a local profile, whether you're aware of that or not, when you start a local pool on your host machine. So what is a profile? A profile is a way for MATLAB to discover as well as interface to a scheduler, right? So it provides hooks in order to do that. And the analogy that I like to make is think about your printer, right? So you may be writing a Word document, and from that Word document, you want to send your document to printer A because it can print both black and white, but also color. But printer B provides the ability to print on the front and the back, right? And so in the Word document, you wouldn't have anything that really describes, well, because I'm going to be sending this to printer A, let's do this, or printer B this. You sort of delineate or differentiate the resources that you need with the code that you want to run, right? So what I'm going to do now is we're going to create a new profile for Truba. Okay, so Jonathan, if you could please post in the WebEx chat the first link that I have here. What we're going to do now is we're going to give everyone access to the Truba MATLAB support package. The support package is a collection of scripts and documentation that we're going to use in order for to create a new profile. Rather than the local profile, we're now going to create a Truba profile. And this information explains to MATLAB how it can submit jobs to the cluster, how it can get the state of the job, and how it can delete jobs. These are the three things that MATLAB has to be able to do. And because MATLAB can do these things, this is what prevents the need for you to connect to the cluster yourself and get the status of a job or delete the job and so forth. Okay, so Jonathan, have you posted the link?
Yes.
Yeah, okay, great, excellent. Okay, so a couple of things that I want to mention. First and foremost, I've posted this support package on our MathWorks FTP site. This link will be good, excuse me, for almost 2 months, right? So plenty of time, excuse me. However, ultimately, really what we're going to do is we're going to post this on the Truba site. I'll be working with the TÜBİTAK folks shortly after this workshop, and we'll get all of this posted onto the site. Okay, so what I'd like folks to do is to click on the link that Jonathan has provided. You're going to log in with the username of Lakeside. And then the password is going to be the number 1, all lowercase letters Q, I, the number 6, R, 4, 7, and the letter F. And if you're able to connect to our FTP site successfully, you should see a link, or you should see a site with these 3 files right here. So to begin with, if anyone is having any problems connecting to the FTP site, please post it in the WebEx chat, and one of the folks from MathWorks will work on it. Will help you troubleshoot it. So let me explain what these files are. The first is getting started with serial and parallel MATLAB, which is a Word document. This is what I was mentioning earlier, will be eventually posted on the Truba site. It describes everything that we're going to do today. The important thing to understand about this getting started guide is that it is what I call a shim doc, which is sort of a bridge between the MATLAB parallel computing documentation, which teaches you about a parallel for loop, par eval, distributed arrays, and so forth, as well as the Truba Slurm documentation, where you understand more about setting wall times, getting email notifications, and so forth. What this Word document simply does is it explains how we're going to create a profile and how we're going to submit jobs to the cluster. It assumes you already know something about a MATLAB parallel for loop, and assumes that you already have, for instance, a Truba account and whatnot. Okay, the next 2 are archive files. They are identical. The file extension dictates whether you should click one for Linux and Mac OS, which is the tar.gz, or the zip file for Windows users. You only need to download one. You don't need to download both. The second is I just want to clarify that when I use the term R2022A, it simply means that when we built this support package for you, we did it using the R2022A MATLAB code base, right? So again, this set of scripts, these plugin scripts, are backward compatible all the way to 17A. So this just tells you the version that I built it on, not the version that is supported. So. Okay, any questions that I should be aware of, MathWorks? Okay, great. So let's talk about how we're going to install the support package. And I'm gonna work with the Windows users, and then I'm gonna work with the Linux Mac OS users. Now, this piece right here is very important. When you download the zip file, it's important that you place it into a very specific location. And the location I'd like you to unzip the archive file is going to be the same location that MATLAB returns when you call user path, all lowercase, one word. This is my user path. Your user path is going to be slightly different, but the reason that we're putting it here is because every version of MATLAB sees this same location. And what this means is that we can install this support package in one location, and if you update your versions of MATLAB, they will see the same version as well. I mean, they'll see the same location, so we don't need to install it in different versions of MATLAB. Okay, so that's the first piece that's important. The second is the way that you install it. So when you extract the zip file, it's important that the contents of the zip file is exactly placed within Documents MATLAB. Most often, when you extract the zip file, you'll notice that it will append for instance, the name of the zip file so that it now is in a subdirectory. And the reason it's important that the files are placed exactly in this location is because this is on your MATLAB path. Okay? So user path is only one folder, and it is on your MATLAB path. What is not on your MATLAB path is slash, non-shared, etc., R2022A and whatnot. If for some reason you've already extracted it and you placed it into a subdirectory, it's important then that you take the entire contents and place it into whatever user path returns. Okay, I'm going to come back to this slide in a second, but I want to flip over now to the Linux Mac OS users. For you, what you need to do is, and actually I'm missing, I apologize, I need to fix one little typo here, number 18-P. So what I'd like you to do is call makedir, and then I apologize, but I'm missing a dash. Actually, you know what? I'm going to put it in for right now. Oh, actually, I can't do it. I'll put it right in here. I'll put right here. So it should be makedir-p tilde documents MATLAB, and that should be lowercase m. And let me just highlight what I was missing there. Okay. So what I'd like you to do is makedir, and then that's a single dash p tilde slash documents MATLAB. And then from there, I'd like you to call tar extract file. And then I'm going to assume that you downloaded the tar file into your home directory, but really you would replace this with wherever you downloaded the tar file from. And then dash capital C tilde slash and then documents MATLAB, just as we typed above here. Once that's done, you can take a look at the listing by typing ls -1 tilde slash documents slash MATLAB. And you should see a listing identical to this right here, or certainly very, maybe it's not color coded, but whatever. Okay, so before we go any further, it's important that everyone is able to successfully do what I've just shown. So I'd like everyone to put a check mark next to your name in WebEx, showing that you've successfully downloaded the support package as well as uninstalled it or extracted it. Okay, I'm starting to see a couple of check marks. That's great. If you're having any troubles at all, please put a red mark next to your name, and one of the folks from the panel will be able to help you out. But I would like to wait just to make sure that everyone has a check mark next to your name. If you can't put a mark next to your name for whatever reason, just put it into the chat, and we'll see that that you're done. So. All right, so I'm only seeing a couple of people with check marks next to their name, so I do want to make sure that there weren't any complications downloading or extracting into the user path. So
I count at least 10 of them, Raymond.
Yeah, okay. Okay. So Jonathan raised a good point that maybe perhaps, so if you don't have R2021B, you should still do what we're doing here, because again, this eventually when you do install 21B, 21B will see this. So good point, Jonathan, but just to alleviate anyone's concerns, if you don't have 21B, you should still follow along with what we're doing. So, Okay. Again, these slides will be made available to you as is the recording. So with that in mind, why don't we continue? All right. So we've downloaded the support package and we've unzipped the archive into the user path directory. The next thing that we need to do is we have to configure MATLAB so that we have a Truba profile. So what I'd like everyone to do is start MATLAB if you haven't already, and then I'm going to ask you to run config cluster. Config cluster is one word, and it is camel case, which means that the first word is lowercase, and then the second word, the first letter is capitalized, so that's a capital C. And I'm going to clear everyone from good. And so when you do so, you will be prompted for your username on Truba. And this is not going to be your university username that you're using at your university, but instead you would have an account on Truba, and that's the user ID that you should use. So obviously, you're going to replace this with whatever is the name of your, whatever your user ID is on the cluster. And let me sorry, let me 1 second. So if folks could put a check mark next to their name once they've called config cluster. Okay, good. I see a couple folks. Now, I was mentioning a moment ago that you need to you can install the support package regardless of the version of MATLAB. However, in order to call config cluster, you do have to now have R2021B installed. Okay, so I'll follow along as well. Great. So at this point, everyone should see something identical to what we have here. Right? So we've got a new profile that's been created called Truba R2021B. And what it's suggesting is that we need to specify the wall time. Right? So I mentioned at the beginning is that MATLAB is going to generate a Slurm job script for us, and it's going to copy it over for you onto the cluster and submit it. One of the requirements to submitting the job onto the cluster is that we specify a wall time, and we're going to do that through this notion of additional properties of the cluster object. But before we get too far, let me just show that the way that you know you've successfully done this is if you go to the parallel menu item on your home tool strip, right? So I'm going to go make sure I'm on the home tool strip, and then I'm going to see a parallel menu item, which is right next to the 3 boxes. And when I select parallel and I just hover over select a default cluster, I'm going to notice a couple things. The first is that not only do I have local, but now I have Truba R2021B. The second thing is that you'll notice there's a check mark next to it. That means it's the default profile. So when I was making that analogy earlier about a Word document, we all have, maybe we have access to multiple printers, but we all have at least, well, we have one printer that is our default printer, right? So that if I'm with my Word document and I hit Control-P to print, if I don't do anything, if I just hit Enter, it's going to automatically send that document to my default printer. But certainly I could change what my default printer is. I could also, within the Word document, I could say, well, I want to override rather than using printer A, I want to send this one time just to printer B instead. So we can specify, we can change our default profile, or we can specify the profile we want to use when we're calling batch, par cluster, par pool, etc. And I'll explain that now. So I'm going to make a call to par cluster, and I'm going to assign it a variable C. It's not terribly important the name of the variable that you call. You know, sometimes I've seen, for instance, cluster equals, or whatever the case is. I'm just going to simply use the letter C for cluster, and I'm going to assign it to the output argument of calling par cluster. And I'm going to use a semicolon to suppress the output. Okay. Now, C is a MATLAB object. An object has properties and it has methods. Right? So properties are different fields, and one of those properties is called additional properties. And MATLAB has tab completion that allows me just to type a couple of letters, and then if I hit the tab button, it will automatically fill in the rest of the name. And what I need to do is I need to set the wall time, and again, I'm going to just type WA, I'm going to hit tab, and that also will autocomplete. Okay, so what I need to do is I need to tell MATLAB to, when I'm creating the job script, that this job will take a certain amount of time. And it's important that the wall time that you provide is reasonably accurate. So what do I mean by reasonably accurate, and why is this important? So if I think my job is going to take 3 hours to run, then I might say, well, I think actually it will take about 4 hours at the most. And the reason that this is important to specify is two reasons. One, first and foremost, if you tell Truba that your job will take 3 hours to run, if your job exceeds 3 hours, the scheduler will automatically terminate your job. So regardless of if you're 80 or 90% of the way done, if you say that your job will take 3 hours to run, and it continues to run after 3 hours, the scheduler will automatically terminate your job and you will lose everything you did during the job. The second reason it's important is because it helps actually to schedule your jobs. Depending on the resources that you need, it's possible that if your job, will say, only needs 10 minutes to run, that the scheduler might say, well, there are lots of jobs ahead of you, right? Because this, keep in mind, this is a shared resource amongst many universities. So there may be other jobs that were submitted before you. However, they require additional resources that the scheduler is waiting on. And if you say you can finish your job in 5 or 10 minutes, the scheduler may consider starting your job sooner than it normally would. So giving it an accurate wall time allows for the scheduler to determine how quickly it can start your job. But on the backside, it's also important that you give it a realistic time so that the scheduler doesn't kill your job too soon. Okay, so the nomenclature of specifying time is seconds, minutes, and hours. And for today, none of our jobs are going to come close to running even 15 or 10 minutes, but just to be on the safe side, we're going to say 15 minutes. Okay, so again, hours, minutes, and seconds. This is another example where it assumes that you know something about the cluster, and if you don't, you should refer to the Truba documentation. There are other ways of specifying. So for instance, if I thought it was going to take 1 hour, I could specify as such, and so forth. So, you know, if you have any questions on the proper way of specifying any of the properties we're going to talk about today, take a look at the Truba documentation. Okay, so so there we are. We're going to set the wall time to 15 minutes. The other thing that we're going to do today is we're going to specify a reservation. And the name of the reservation is called MATLAB, and it's only good for today. I think maybe it expires tomorrow, I'm not really sure, but let's assume it's just for today. And this is going to help ensure that our jobs start sooner than they typically normally would. The folks at TÜBİTAK were kind enough to create this reservation for today, just so that we could get our jobs submitted through, because they knew it would be quick. But after today, you would not use this reservation, and you would have to follow the normal scheduling policy. All right, so the last thing that we need to do is save our profile. Okay, and the reason that we save our profile is because if we don't save the profile, what we're typing here is temporary until MATLAB exits. Once MATLAB exits, if we didn't save the profile, then these properties would go back to their default values, which is empty and empty. All right, I'm going to pause there for a second. Hopefully everyone's been following along with what I've been doing, but I want to just check to see if there are any questions I should answer. Excellent. All right, so we're now ready to submit our first job. The one thing I would say is calling config cluster is only done once. Its only responsibility is to create this profile. Now, anytime you start up R2021B, the profile will always be there, so you only need to call config cluster once. All right, we're going to be focusing all of our time on the batch command, not the parpool, but I do want to just make some differences between parpool and batch. Parpool is typically when you're running things locally and you want to have an interactive session where we start the pool of processes, or again, what we call workers, but where we then can call parallel constructs like par4, par-eval, and so forth. It's a synchronous execution, which means that you can only have one parallel pool running at a time. The way that things are designed, parpool will not work from our machine to the cluster, because it requires that the workers running on the cluster can communicate back to your host machine, which for all intents and purposes is not feasible. What we are going to work on today is the batch command. The batch command has several advantages. First of all, because it's a non-blocking command, it allows us to be able to submit multiple jobs at the same time. And I'll show you at the very end one way that we could have almost like a job launcher and so forth. But the second thing is that it doesn't require that the MATLAB client is running or our laptop or desktop. So we can shut MATLAB down, and then we can shut down our laptop and so forth. We can reboot our computer, we can restart MATLAB, and then we can get the results of running our batch job at a later time. And I'm going to show you all how we do that through the API. Okay, for those who are not on the network, you will need to VPN in at this point if you haven't already and need to. So you should do so now. So let me just VPN in. All right, so here we are. We're ready to submit our first Hello World job, right? So what we're going to do, something actually that's very simple, but it turns out it's a very important piece of information, and that is when we're running MATLAB on our host machine, we know exactly where MATLAB is running, right? If I just type pwd, that tells me the present working directory, right? And so it might be in my C drive, or maybe it's in my /home/Raymond, but we know where MATLAB is running at that time. But if we're going to submit a job onto the cluster, would we even know where MATLAB is running on the cluster, right? And the reason that's important to understand is because if we're reading files from our current location, or if we're going to write files to our current location, it's really important to understand our environment. So let's go ahead and submit our first Hello World job here. Okay, so we're gonna we already have a cluster object, and we're now ready to submit our first job. So I'm going to type job equals c dot batch at, and what I'd like everyone to do is just follow along with what I'm doing, and then I'm going to explain what everything is. Okay, so job equals c dot batch, left parenthesis, at pwd, comma 1, comma, left curly brace, right curly brace, comma, single quote, current folder, and you can type CU and then hit the tab and it'll auto-complete, comma, single quote, period, single quote, right parentheses, semicolon, and then enter. Okay, so if you've done that successfully, then you should be prompted regarding your SSH credentials. So MATLAB's going to generate a job script and submit it for you on the cluster. In order to do that, we need to be able to S-copy the files over and then SSH to the cluster for you to run those commands. So we already know who you are because we prompted you for your username. What we don't know is how we're going to authenticate you. And we can do that either through a private key, or what's referred to sometimes as an identity file, or through your password. So for me, I don't have a private key, and I would assume that probably most folks do not. So I'm going to click that I am not going to use an identity file. And instead, I will now be prompted for my password. So at this point, I'll go ahead and all right. So I don't want to go any further than this until I find out that everyone has been able to do it exactly what I've done as well. So I'm going to clear everyone's markings. And what I'd like everyone to do is just take a moment to put either a green check mark next to your name or a red mark. So a green check mark means that you called the command exactly as I've written it here. You were prompted for your credentials, and you get a line that says additional submit args equals, and you have this output here. If you ran into any technical issues, you should put a red mark next to your name and then list what the issue is. And let me take a moment to look at all right. Okay, we have to change. So there was a question: do we have to change the cluster host to? We do not. The cluster host of 172 should work perfectly fine. There's an error that says access denied to requested reservation. Okay, so if for some reason folks are not, if they get an error message saying that you have not been added to the reservation, then simply type, so go back to c.additionalproperties.reservation equals, and then make this the empty string. So it would look like c.additionalproperties.reservation equals the empty string, hit enter, and then save the profile. The truth of the matter is that most likely these jobs will start quite quickly anyway, and it's not imperative. And again, after today, you wouldn't have access to this reservation anyway. Let's see. Could not connect to remote. Contact the cluster. Okay. All right. So could could someone perhaps from the TÜBİTAK take a look at Mustafa's question? They could not connect to remote host 172. Mustafa, I'm assuming, of course, that you either don't need to VPN in, or you do, and that you have VPN'd in. Is that correct? Okay, so Selçuk is saying that if you're on the campus, you do need to. So Selçuk, you're saying that you cannot use the 172 address. You have to use Lebrick 1. Okay, so when we built this out, because I do VPN in, I use the 172 address. What I'm hearing is that are you using the so Mustafa, I was running through the exact same issue actually yesterday. What this says is that the clock on your desktop machine is ahead of Truba, and so this says it's 11 seconds. What I noticed is that yesterday, when my desktop machine was within 3 seconds, that it worked fine, and then eventually it did. Synchronize. Okay. Bear with me for 1 second. So I think I might be able to help you. I'll show you what I did yesterday. Let me just go to let's see. So, folks, I'm just going to take a moment to help Mustafa for a second to help fix his clock. For 1 second. Actually, what I'm going to do, Jonathan, I'm going to put in the chat, in our internal chat, I'm going to put what you can find for him. So, Jonathan, I just put in our chat the location, and in there you're going to find 2 scripts. There's a okay, so Jonathan, if you're on the Truba VPN or TÜBİTAK VPN, you should get off of that. Okay. Go to the what I put into our internal chat. Go to that location. In there, you'll see two scripts. One's for laptop, one's for desktop. Find out from Mustafa whether they have a laptop or a desktop, and then look at the contents of those two files, and then post that into the chat. It's a bunch of Windows. Well, okay, I should say, Mustafa, what Jonathan's going to send you is for Windows. If you go to time.is, it'll tell you whether your clock is off also as well. Thank you for the reminder, Jonathan. All right, so let's, with that said, let me continue. Yep, okay, thank you, Sifa. So Sifa was saying you can run ntp date command if you're running on Linux. Okay. So thank you everyone who's helping out to try to resolve that. So, all right, let me go back to sharing the screen here. Okay, so at this point now, and this is actually sort of a good example of your workflow, right? So you're going to submit a job to the cluster, but the question now is my job finished? Has it even started running? And if it has, what's the results and so forth? And the way that we're going to orchestrate all of that is through the job command. The job object. Job object has also, as I mentioned, an object has properties and methods. And so the first property that we want to find out is job.state. Okay, so anytime when I'm using a MATLAB object and then I use the dot notation, that allows me to start typing some letters and then using tab to autocomplete. So anytime you see me, if I'm typing, job dot, and then if I hit the tab key, this tells me all the options that I have and so forth. If I hit escape, then that will remove my listing. Okay, great. So I've submitted my job using the MATLAB batch command. I've had MATLAB query the state of the job to tell me whether it's queued, running, or finished. It tells me it's finished. Now, the last thing I want to do is I want to fetch the outputs. And for this, I'm going to type job.fetchOutputs colon, left curly colon, right curly. All right, so I've done a lot here. And as I mentioned, I wanted everyone to follow along with what I'm doing. But now I'm going to go back and I'm going to sort of, I'm going to unwind and explain everything that we've just done to this point. Okay, so the C variable is a cluster object. I mentioned that it has properties, like additional properties, and it has methods like batch. So what do I mean by properties and methods, and how can I differentiate one from the other? A property you can almost think of as being like a field or a name, and it's easily identified by the fact that it starts with a capital letter. So it's a sort of a programming pattern or a design pattern that for MathWorks, when we create objects, the properties start with a capital letter, and the methods or actions or verbs start with a lowercase letter. So that's how you can tell the difference between one and the other. Okay, so we're calling the method, which is batch, which is going to submit this job. There are multiple types of input argument, or there's multiple ways of calling batch. I'm going to focus primarily on this format, but I'll talk about a different format a little bit later. So in this format, what I'm going to do is I'm going to first specify the function that we want to call. The function, in this case, is PWD, print working directory. Now, what's important is that we're using the @ sign in front of PWD because this makes it a function pointer. And a function pointer delays calling this function until a later time. So I'm not going to do this right now, but imagine, for instance, if I were to say, j equals c.batch, and then I say PWD. Well, in this case, and with the other input arguments, in this case, it would first call PWD, which is in my C drive, and then take that information and then pass it to the batch command. Well, of course, that's not what I want to do, right? What I want to do is I want to tell batch the command that I want to call on the cluster is PWD. And the way that we do that is we pass in a function pointer. For some of you who've been using MATLAB for a while, you may know that this is referred to as a function. It is a MATLAB function that takes as an input argument another function. All right, so we're going to pass in the function that we want to call, a pointer to it. The next input argument is the number of output arguments that this function is going to return. Now, what's important is that your function that you write might have 4 or 5 output arguments. However, for good reasons, you may only want to return 1 or 2 of those output arguments. You could imagine that your function returns a pass failure, but it also then, as a second output argument, returns this million by million image that you don't want to have returned. So we can't just look at your function and determine that it has 2 output arguments and assume that you want both output arguments returned. So you need to explicitly tell us how many output arguments that you want to have returned, including perhaps 0. You may want to call your function that has 5 output arguments and you don't want any of them returned. The next is a MATLAB cell array, which is going to be a comma-separated list of input arguments that are going to be passed to calling your function. Now, PWD, which is print working directory, of course, doesn't take any input arguments, so our cell array is empty. But to give another example, imagine if maybe, and you don't have to follow along with this, maybe what I want to do is I want to do some portfolio analysis, right? And maybe it's going to have 2 output arguments, excuse me. And what I'm going to pass in is Apple, and maybe I want to pass in another Microsoft. I don't actually know what I think that's Microsoft. But then I might also say, well, I want to go back 30 days. And I want to do it for, maybe, some other information such as, you can imagine, skip Sundays or whatever the case is, right? So the point is that when we're calling our function, we need to pass as our third input argument to batch is going to be a cell array of all the input arguments that are eventually going to be passed to your portfolio analysis functions. Okay, so at a minimum, this is what's required. And I'm focusing primarily on functions. We'll talk about scripts because certainly a lot of MATLAB users write scripts. We'll talk about how we would call a script and the differences in calling scripts versus functions. But for the time being, we're going to call a function. All right. The next input argument is setting the current folder. Now, you'll see in the next slide what happens if we don't specify the current folder, but in this case, what we're going to do is we're going to specify it to period, which means our home directory. All right, so there it is. We've specified that the function we want to call, how many outputs we want to have returned, a cell array that would contain any and all input arguments that we're going to need to call our function, and then we're going to specify that the current folder should be starting in our home directory, which in this example tells us exactly really what PWD is going to return, right? We're telling MATLAB to start in our current folder in our home directory simply by specifying our period here. And again, I'm going to talk a little bit more about current folder in a second. Okay, so what you'll see is displayed a partial list of the Slurm argument list. For those who are familiar with Truba or your own cluster and particular Slurm or maybe any other scheduler, you'll know that when you're creating a job script, there are going to be certain parameters that are being passed to the scheduler. And so in this case, we can see that we want a single task. It's going to run on a single node. It's going to request 28 cores or threads. And Michael was talking about this, and I'll talk more about this in a few slides, because this is a very important consideration when we're submitting jobs to Truba. And then we can see that we specified 15 minutes, our reservation, and that we're running on the Hamzi partition, which again is very important to understand when it comes to the number of cores we're going to request. Okay, so I'm going to move along a little quicker here just to keep us on track. But notice that since the state of the job is finished, we can now get the results, right? So everything is going to be using this job object. We assign it by calling batch. We're going to get the property state, but notice that if we want to get the results of calling that, we're going to call the method, and so that's why it starts with a lowercase f. And then we want all the outputs. So the outputs could be of different types, so that's why the outputs is also in a cell array, and so we're indexing saying that we want all of the outputs. In this case, there's just one, and that the answer is Truba home. For me, R Norris. For you, it would most likely be Truba home, whatever your user ID is. Okay. So I'm curious if folks had any issues up to this, or let me do this the other way. Was anyone able to successfully fetch their result and get something similar to this? Okay, so I see a couple of folks. Okay, great. Did anyone run into any issues that have not been addressed to this point? Okay, not seeing any X marks. Okay, good, excellent. All right, so let's go on. As I mentioned, calling par cluster. This is what gets us our handle to our Slurm object, and then calling the batch command is what's going to generate our job script that we submit to the cluster. So, all right. So let's talk a little bit more about current folder. In theory, you don't need to specify the current folder. If you don't, then when you fetch the outputs, you'll get an error message, or I beg your pardon, a warning message similar to what we see here, which is that when you submit a job to the cluster, MATLAB has to start somewhere. And so it just says, okay, well, why don't we start in the same directory I'm sitting in on my host machine right now, which when I submitted this was in the C users directory. Well, C:/users doesn't exist on the cluster, and so therefore the job will be executed from Truba home R Norris, which is my home directory. And so to avoid this warning message, you can specify the current folder to period. Now, what you also could do is you could set current folder to be, we'll say Truba home R Norris /proj5/January, right? So you could set it to any valid directory, and that's where MATLAB will start. If you don't specify, if you don't care where it starts, then you could just use period, and it will start in your home directory. And if you don't mind the warning message, well, then you could leave off the current folder. But in all the examples you'll see this afternoon, you'll see that we use current folder set to period. All right, so that's our first sort of hello world example. What I'd like folks to do now, so Jonathan, if you could post the link to the workshop content. Again, we will also post this content on the Truba site at a later date, but you will have access to this now. You should still be logged into the FTP site, but if you're not, you would use the same Lakeside account to log in. So I'm going to ask everyone to take a moment to log into the FTP site, specifically to this tiny URL, and in doing so, you will see a list of workshops. Same thing, you only need to download either for Linux, Mac OS users, or the zip for Windows users. So go ahead and download the appropriate zip file, or I beg your pardon, archive file. And take a moment to do that. Okay, so let me walk folks through where we're going to install the workshop files. So similar but not identical. For the Windows users, we're going to install it into user path, but for this, we're going to actually create it in a subdirectory so that when you install it, it should actually get extracted here. And so that means that you will now see a subfolder called MATLAB-workshop. Okay, so we don't want it. We don't want to extract it. Actually, we don't want all the contents of that cluttering the your documents MATLAB folder. But instead, we're going to create it. When you extract it, it will automatically create a folder called MATLAB-workshop. So I'll do that again. Let me go. So we're going to take our zip file. We're going to extract it here into user path, and when we do so, it will create a subfolder called MATLAB-workshop. Let me flip over to the Linux users. So we should already have the documents MATLAB directory, and in this case here, we're going to tar extract file / MATLAB-parallel-workshop .tgz, and then -C / documents MATLAB. And if we take a look at MATLAB-workshop, we will see a list of some of the files that we'll use today. Okay, let me go back just for the Windows users, and a check mark next to your name, please, once you've gotten this far. Excellent. Great. So let's jump back over to MATLAB. And what we're going to do now is we're going to, sorry, there was a question. Jonathan, did you see the question that was posted? I think there was a question as to where to get the files. Did you see the posting, Jonathan? Yeah. Okay. So so there was a question, where do we get the MATLAB parallel zip file? And so Jonathan had posted, I believe, is that right? Was that maybe not. Okay. Okay.
Is it in the same FTP directory than the support package, Raymond?
It's not. I'll post it in the URL. So I've put into the chat the tiny URL. So by clicking on that and then going to, Alex posted the username and password as a reminder. And so in doing so, you should see, excuse me, you should see TÜBİTAK workshop, and then you will see the zip file and the tar file. So, all right, great. All right, so I mentioned that by placing this as a subdirectory, that this will not be on your MATLAB path. So in order to get access to these files, what I'm going to ask you to do is to CD to full file user path MATLAB-workshop. Okay? So full file, it concatenates user path and MATLAB workshop. And when you do that, you should, within the MATLAB environment, you should see all the other workshop files. All right. So we're going to focus on one example today, which is estimating pi, or calculating the area under the curve to estimate pi. And there's actually a couple of ways that we could do this. Last month we focused a lot on par 4. I just want to explain a little bit more about what an SPMD block is, and so I'll show you that in the next slide. But really what we're going to do is by calculating pi, we're going to segment the curve into n number of processes or workers. So in this case here, what we're going to do is we're going to take the integral from A to B, A1 to B1, A2 to B2, etc., and then sum up our integrations to get to calculate pi. Right? All right. So the way that we're going to do this is using an SPMD block. Now, we could write a parallel for loop to do the same, but again, I want to focus a little on SPMD and how it works. So an SPMD is single program, multiple data. It's highlighted in blue, which tells us that it's a built-in keyword, and it is one of our two main parallel constructs. The other one, of course, being par 4. Where par 4 is how do we run code faster, SPMD typically is focused more around how do we work with distributed arrays and so forth. All right, so we're going to calculate our lower bound and upper bound of our integral by chunking our curve. And the way that we're going to do this is using lab index and numlabs. Numlabs is the total number of workers. And we'll talk about how to start a parallel pool in a moment, but let's just say, for the sake of discussion, that we've started up 4 workers. So the MATLAB function numlabs will return the number 4. Lab index is the way that we identify any one of those workers. Sometimes this is referred to as the worker's rank. Okay. So lab index will return either 1, 2, 3, or 4, right? Because there are 4 labs. So lab index 1 minus 1 is 0 divided by 4 gets us 0. And lab index of 1 divided by 4 gets us a quarter, right? So this is all running on worker 1, but it's also all running on worker 2 and worker 3 and worker 4 all at the same time, right? So this code is being run on each of the workers. It's going to have a different value for A and B because the lab index is different. This will go from 0 to a quarter. Worker 2, 2 minus 1 is 1 divided by 4 is a quarter, and 2 minus 4 is a half. So it'll go from 1 quarter to 1 half, and so forth. All right. We're then going to print our subintervals, lower bound and upper bound. we're then going to take the integral of our quadratic, and then we're going to pass in our lower bound and upper bound. Again, this is happening on each one of the workers. Much different than a par 4, which also operates on different workers, but this is all happening at the exact same time. My integral will be the local integration from A to B, right? It's going to have a slightly different version, value for each one of the workers. So A and B are unique. My integral is also unique for each one of the workers. And here we will print the lower bound, the upper bound, and then what the integral is for that segment. The last thing that we need to do is we've got these individual summations or individual integrations. Now what we want to do is we want to sum all those integrations together. And then we're going to do that using a global operation called G+. So G is global, and plus is the operation that we're doing, right? So a global addition, and we're going to globally add my integral. All the workers are communicating to each other, and in all likelihood, what's probably happening under the hood is that everyone is sending their value to lab index 1. Lab index 1 is probably adding all the values, and then it's broadcasting the results back out to all the workers so that pi approximate is the same value on all of the workers. So we have unique values for A, B, and my integral, and we have replicated values from pi approximate. The SIMD block has a built-in barrier that will not continue until all the workers have finished running. Actually, it has a barrier at G+, because we can't do a global operation here until all the workers have calculated my integral. To finish this off, we're going to, outside of the workers that are running right here, now we're going to assign a variable called approx1, and we're going to assign it to pi approx, which is right here, and we're going to index into the first element. So pi approximate is a 1×4 cell array because there are 4 workers, but because they're all the same value, all we have to do is index into the first element. And then we finish off simply calculate or displaying what MATLAB says pi is, what our approximate value is that we calculated, and what our error rate was. The last thing I would show you is that if you look at integral and we're passing in the name of a function, using a function handle, which is described down below here, that's just like what we were doing earlier with the batch command, right? So batch at the name of our function. So this is a delayed call to quad pi because we're passing in a pointer to that function rather than actually calling quad pi right now, which we wouldn't want to do, obviously. All right, so let's talk about, now that we have our code, let's talk about where are we going to start our parallel pool, right? So I'm going to take a slight tangent here for a second. In this example here, for par 4 I equals 1 to 8, we're going to create a variable A, index into it with IDX, and assign it to RAND, right? So pretty simple. So the question is where do we start our parallel pool? So what we learned back in June is that actually a par 4 will automatically start a parallel pool for us if one hasn't started. But it's possible that we want to override the default number of workers that starts up by explicitly calling par pool. Well, the problem here is that when we call our function, we start up a parallel pool of 4 workers, and now we run our parallel for loop, and then we said, oh, actually, instead of 8, we wanted to make it 16. So what's going to happen the next time we run this code? Well, as we remember last month, if we try to call par pool a second time, we will get an error saying that we've already started an interactive session. You can only have one parallel pool running at a time. So it's not a good idea. It's not a good recommended practice to make explicit calls to par pool within your code. And I was talking about this earlier, that you want to differentiate or separate rather the resources that you need, like compute, with your actual code. So if we're not going to embed the call to par pool within our code, where do we start the parallel pool if we want to call it explicitly? Well, we can do it from the command window, right? The command window, we can call par pool. We could have MATLAB automatically start it, we mentioned that, or in the lower left-hand corner, we know that there's an icon that we can click and we can start parallel pool. So there's several ways that we can start that parallel pool without actually needing to explicitly call it from within the code. All right, so if that's the case, then how are we, when we call the batch command, how do we specify the pool size? And the way that we do that is we're going to include a pool argument to our batch call. And the pool flag will take the size of the pool that you want to start. And by default, if you don't specify a pool, the size of the pool is 0, which is perfectly legitimate. There may be many times that you simply want to offload your code onto the cluster, but haven't actually parallelized your code, and there's no need for a pool of processes. All right, so now jumping back to calculating pi, let's jump over to clear this. So now we're going to call assign job. Let's say job 2 equals c.batch. Actually, I need to bear with me for 1 second. I have to. All right. So job 2 equals c.batch at, and then calc pi. It's going to have 0 output arguments. We're not going to pass in any input arguments. We're going to set the current folder to period, and we're going to specify pool size to be 3. Now, I'm going to explain a little bit later in more detail about this, but the size of the pool, as Michael was mentioning during his presentation, it's very important that your job fits on the node, on the HEMC node. And so there's actually a unique number of workers that you can request so that it evenly fits into 28 cores on a socket. I'm going to go into a lot more detail about this in a couple of slides, but for the sake of discussion, notice that when we specify a pool of 3, that we're requesting actually 4 tasks, and that's always going to happen. So the size of your pool, if you specify is 3, then we're going to add 1 more for 4 workers. And the reason that we do that is, let's go back to the code here. When we specify a pool argument, all we're saying is how many workers should be dedicated to your par4 or your SPMD block and so forth. But we need another MATLAB process that can run the serial code. So notice that we can interweave parallel and serial code together in one file. But in order to do that, we need an additional MATLAB process that can run the serial code, as well as also send these instructions to each one of those workers to run and so forth. All right. So, right, if the size of the pool is 3, then we're requesting 1 additional one. Okay, so at this point, let me explain a little bit more about what I'm going to sort of call the power of 28. And so it's important to understand that the Truba cluster is comprised of many nodes, and each node is comprised of 2 sockets. And a socket is what we place a CPU in. And then that CPU has even smaller components called cores. And there are 28 cores per socket. The way that the scheduling policy has been created for running jobs on Truba is that MATLAB has to run on the HAMZ partition, or queue, primarily, primarily because the versions of the operating system that MATLAB requires are only on HAMZ. All right, so on the HAMZ partition, and we put this into your job submission. You don't have to specify the partition. We do that for you. But it does require that your job, or that multiples of 28 are being consumed by your job. So the way to think about this is that the number of workers that you request either have to be a factor of 28 or a multiple of 28. And I mean the total number, right? So if you're requesting, I'm sorry, folks, let me. If you request a pool of 3 workers, we are really going to ask for 4. 28 divided by 4 is 7, and so therefore what we will do is we will assign 7 computational threads to each one of the workers. So one worker gets 7 computational threads times 4 workers is 28. I'll talk about more than one node in a second. If you, however, specify a pool of a number that ultimately is not evenly divisible into 28, or a multiple of 28, then we throw an error message saying that the prox per node, which is 28, must be evenly divisible by the number of workers. And again, keep in mind that the pool of 2 is really 3 workers, and 28 is not evenly divisible by 3. Likewise, if you request more than 28 workers, then the number of workers has to be a multiple of it, right? So 55 plus 1 is 56, and so therefore we will request 2 nodes. However, if you were to request, we'll say 30 or 40 workers, then we'll tell you that the number of workers, which is 31, times the number of threads must be evenly divisible by 28. It got lopped off here, but you would see that in the error message. Okay, so with that said, let's keep going here. So we've submitted our job. Now we want to get the state of the job, and we see that that the state, again, that's a property. It starts with a capital letter. Is finished, and so now we're going to go ahead and fetch the results. But notice that when we fetch the results, that nothing came back. So the question is, if we ran our function, why is it that we didn't get any outputs? And the reason is because we explicitly told MATLAB that no arguments should get returned. Even if the function did return some output arguments, if we specify that none should be returned, we won't see any. Okay, so now let's start talking about then how do we get results back? You know, what are the different things that can be returned, and how do we go about doing that? So there can be function outputs could be returned. The diary could be something that returns output or results, as well as saved files. And we're going to look at each one of these. So we'll use this as an example, test_FCN. We're going to pass in the number of simulations that we want to return, that we want to run, and then we're going to return a time argument as well as a matrix A. We're going to display that we're going to start the simulation. We're going to assign T0 equal to the timer, so we're going to start our timer. Par4 IDX equals 1 to the number of simulations that are being passed in. We're going to assign A. This is going to be very quick, so we're going to put a pause in for half a second. We'll display IDX, and then once we're done with our par4, we will finish, we'll get the time, which will get returned. And then we'll display that we've finished our simulations, and we will save the A matrix into a map file called results. All right, So here we go. We submit our job. We're going to pass in 300, which again is the number of simulations that we want to call. We're going to specify a pool size of 6. So again, there's very specific number of pool sizes that we can request. A pool size of 6 is really 7 tasks. 28 divided by 7 is evenly divisible by 7 means that we're going to assign 4 computational threads to each one of the workers. All right, so the job has finished. We go to fetch the results, and we get a time of 27 seconds. So again, why aren't we getting the A matrix? We assigned, we specified in our prototype that test_FCN returns time T in matrix A, but the reason is because we only requested when we called batch that 1 output should be returned. And this is a common scenario where instead of, again, T, it could be a status where we just need to know if something passed or failed, but we don't necessarily need the A matrix. The problem is that maybe something failed and we wanted that A matrix, right? So how could we go and still get the results? So I'll show you that. So the next is that we could look at the diary. The diary is displaying the diary is a method, so job.diary will display anything that the MATLAB client running on the cluster would have run. So here we can see that we started the simulation. We can see that we're printing out IDX. And notice that 4, 5, 8, so it's not printing out 1, 2, 3, 4 all the way to the number of simulations, because the par 4 can run in any order, right? And so forth. So what I didn't display everything, including that it was finished, but the diary is a really good way of being able to troubleshoot your code to see how far you were able to get to run. All right, so the last thing that we could sort of return is files, right? So until our 2021B, there was no way of being able to pull files back to your client. In 22A, we started creating what's called a data store, value store and a file store, beg your pardon, a file store. And with a file store, we can actually pull files back. But because we're using 21B here, we don't have the seamless ability to copy files back. So what I'm going to do here is I'm going to store my A matrix into a mat file called results. But the question I have is, where exactly is results being written to? And the answer actually goes back to the very first example that we ran, which was PWD. If we don't explicitly specify where the results should be written to, then it's going to be written to wherever the MATLAB is being executed on the cluster, which we know is either your home directory or whatever you assigned current folder to, right? So the reason this is important is because at some point I need to use my FTP client to copy the files back, and I need to know where I can find it. Okay, so let's move on. There are other properties actually that you can specify, I'm going to probably make an adjustment to the cluster host, and I will let folks know once that's done, because most folks probably don't need the 172 address. They could use the fully qualified domain name instead. So I'll get that updated, and that will get pushed out. And then you'll just need to download that, put that into your user path, and you'll be good to go. And then I'll send out some additional instructions for that. So, all right. But really the main things that you're going to need to set is the wall time. The email address is what we'll talk about in a minute. Okay, I want to transition now to going from functions to scripts, because I do think that a lot of people write MATLAB scripts rather than functions. So I'm going to talk about the behavior that you'll see when you're calling scripts. For starters, this is probably an unconventional way of writing a script, but what I've done here, I simply just embedded or inlined in these quotes the code that I want to run. But you could imagine that I could replace all of this with simply just the name of my script, which could be, my script. That's it. Now, because it's a script and not a function, the first thing you'll notice is that there's no, we don't specify the number of output arguments, and there's no input argument list because there's no function header or no function prototype there that specifies those things. Now, instead, what we do is we're going to look at all the variables that are in your base workspace or college workspace, and we're going to pass those with the job. Likewise, because we don't know what variables you need passed back, we're going to take all the variables that were created and we're going to pass it back to the MATLAB client as well. And so, as you can imagine, this could be very costly, right? Imagine that I've got some very large matrix, right? So here I have z equals rand of 3, but imagine this were, a million by a million, right? Well, this might be something I'm doing on my local machine, but you can see that nowhere in my script am I actually referencing z, but MATLAB doesn't know that. So this variable z is going to automatically be attached to the job. And ironically, it's also going to have to come back because perhaps I need z as well. So all variables are sent back when you're calling a script. So let's take a look. We're going to clear our variable z just to show what happens. So actually, let me explain here. So job equals c.batch. The script that we want to call, which again, you don't need to, obviously you don't need to inline. This could just be, my script. We'll set the current folder to period. And number of tasks is 1 because pool is not specified. So it defaults to 0. 0 plus 1 is 1. So a single task with 28 threads to run this code. We're going to clear z, and so we can see that the only variables are now c, job, and x. We get the state of the job, it's finished. And now to get the results back, we don't fetch the results, but instead we're going to load the job. When we load the job, it's like loading a mat file, because that's almost what we're doing. We're loading all the variables that we stored from the job. And here we can see that we have ants, c, job, temp. There's, here's temp and z. So the question is why are we getting z? We cleared z, but now when we look at our workspace, it's brought back. And that's because we assigned or we passed a z to the job, and so therefore everything needs to come back, so that includes z. Well, what about temp? Temp was never, we never even created temp in here. I'm sorry, I beg your pardon. We did create temp here, and so therefore this temporary variable that we didn't actually need brought back is also being brought back to our base workspace. So we can see that by not using functions, we sort of lose this contract that we have that specifies what variables need to be sent to the job and what variables need to be brought back. And it's possible that that could be a very costly action. So as a strong recommendation, I would suggest that you always write functions, not scripts, which may require a little rework in your code, and I'll talk more about what that looks like later. Okay, so some other things to think about when we're submitting jobs to the cluster is how do we go about specifying the paths? Should we attach files? Should we set the client path and what have you? And so, if as a rule of thumb, the fewer number of files that you can attach to your job, the better off. When MATLAB is going to submit the job to the cluster, it will automatically attach files that it needs on your machine to the job. Well, because you can run lots of these jobs, you can imagine that now each time that we're submitting the same job, every time we've got to go through and find all the files that are required to attach to the job. So if I had to do a loose rule of thumb, I might suggest that if your job needs 5 or 10 of the files that you've written, then I would consider maybe just having MATLAB automatically attach those files. But if you've got 40, 50, 100 MATLAB files, maybe you've written your own toolbox, what I would suggest is taking those files, copying onto Truba, and then pointing the MATLAB client to where it can find those files on the cluster. So that way, when you're submitting your job, you're only submitting a few number of files to your job. Okay, I mentioned that you can specify email notification when your job has started and when it's going to finish. And this is very helpful for you folks, because when you're submitting a job from your machine, you really would have almost no idea when your job's going to start, and more importantly, when your job is finished. Because you can quit MATLAB and shut down your desktop machine, we can log in, we can restart your machine and start MATLAB tomorrow once you've gotten email notification that your job has finished and so forth. So the question then is, okay, how do we go about getting the results from a job that we ran several days ago? One of the things that you can do, going to the parallel menu items, you can go to the job monitor. The job monitor allows you to select any one of the jobs, and then you can either fetch the outputs, or you can look at the error files and so forth. So it's not required that when you use the MATLAB batch command that you keep MATLAB running all the time, or that your desktop machine is running all the time. You can shut all that down, restart MATLAB another day, and get the results. It is a good practice to delete the jobs that you don't need anymore. Because we use the file system to track all your jobs, as you submit more and more jobs, it will start to slow MATLAB down if it's got to parse through all the files on your local file system that you've run in the past. So as you have run jobs and you no longer need the jobs, at some point it's a good idea to delete the job. The delete method, or delete is a method of job, so you can type job.delete. You can also, using the job monitor, you can go over and you can click delete there as well. All right, we're at the top of the hour. If you don't mind, I just have maybe another 4 or 5 slides that I can go through quickly, but I just sort of want to finish off talking about how we can go troubleshooting and debugging. So I'd love to say that all things work all the time, but in fact, sometimes jobs do go awry, and it's important to work with the TÜBİTAK folks to understand, for troubleshooting and so forth. So first thing that they're going to want to know is what is the scheduler ID of your job. MATLAB has this notion of a job ID, but Slurm would have an entirely different value. So when you're putting in a help ticket, you would not tell them what the MATLAB job ID is, but what you need to know is the scheduler ID. So by calling job.getTaskScheduler IDs, this will tell you the Slurm job ID. So that's the first thing that they need to know. The second is any error messages that MATLAB might have captured. So if your job throws an error, when you fetch the results, MATLAB will display what the error is. Now, it's possible that that error is something that you could fix. Because maybe you've given an invalid, incorrect name or what have you. So it's just resubmitting the job. Other times it might be because there's a licensing issue, and I'm going to talk about that in the tail end. And so for that, they need to they'll want to get a capture of the log file. So the way that we can capture the log file is by making a call to get debug log, and getting the log file will display whatever Slurm wrote to disk. So this will be something else that you want to put into the help ticket. All right. I want, just as a reminder, for you to remove the reservation. So at this time, bring up MATLAB and type c.additionalproperties.reservation equals empty string, and then save that profile. So that way, for future jobs, you won't be using a reservation that's no longer valid. So I'm going to skip over this piece here. It just talks about some of the things to think about to make your code more robust so that it works when you're running jobs on the cluster. You have access to these slides and the notes, so feel free to take a look at here. The last couple of slides here, I just want to talk about, if you start thinking about, you now really have this way to be able to run jobs at bulk. And so you could imagine that from your MATLAB client that you could have a for loop that says, okay, here's the code that I want to call, and I'm going to pass in a collection of different input arguments, And now we can start launching, 5, 10, 15, 20 of these jobs, right? So ideally, you want to get your code to run as quickly as possible, but you may have multiple data sets that you want to be working with. And so now you have the ability, all within the MATLAB environment, to be able to launch those jobs onto the cluster and then stay within the MATLAB environment to get the results and do post-processing and so forth. So in this case here, maybe we're going to submit 4 jobs, and I'm going to wait for the second job to finish, and then I'm going to get the time that it took to run my second job and so forth. So this is just a very crude example, but it sort of gives you one idea of what you could be doing with the batch command. And the last slide that I want to talk about actually gets back to Michael's second to last slide that was talking about performances and so forth, and the trade-off of using something locally versus using Truba. So the things to think about is, in Michael's case of the workstation, certainly the advantages of using a high-powered workstation is that you get, probably immediate access. I say, probably because maybe other people are using the workstation, but if no one's using it, then you'd have immediate access to it. And licensing is certainly a little bit easier because it's all within the confines of your university and so forth. Probably the drawbacks is that you have to think about the cost of procuring, the cost and procuring additional workstations and so forth. And then what happens to the workstation when it's not being used? So you paid up front for using that workstation, but what value do you get from it if it happens not to be being used? And it can only run one person at a time because of that. If you wanted more people to be using it, then you'd have to procure more workstations. Conversely, using something like Truba, the advantage is that there's an enormous number of nodes that you have access to. And because of that, you have the ability to run many jobs, or at least submit many jobs at a time using the batch command, and then let the scheduler figure out when it can actually run your jobs. The drawback could be that, depending on the workstation, it's possible that the workstation may be more powerful than on one given node. But again, you have lots of nodes that you have access to. So it's, certainly you have a value with running on Truba. On the last slide, which is the next one, I'm going to talk about configuring your MATLAB licensing because there is a piece there. Today, we've been using a trial license for MATLAB Parallel Server. I'll explain in a second what you'll need to do if you want to get started as well. And then obviously, you need to transfer files and data over to Truba, which you'd have to do for the workstation anyway, but maybe it takes a little bit more work to do that. Okay, so last slide, how do we get started? If this is something that you would have an interest in doing, first and foremost is that you have to have Truba be able to find your Parallel Server license. And the best thing to do is to get in touch with the Truba folks. They can get in touch with us as well, and we can help configure, because your universities do have MATLAB Parallel Server. We just need to have Truba point to your Parallel Server license, and then you'll have access to this as well. Okay, so we talked a lot about this afternoon. I apologize, we ran a few minutes over, but really the key takeaways are that we call config cluster in order to create the Truba profile. That we need to, we'll prototype our code locally on our host machine, but then we'll use the Truba profile to be able to submit multi-core and multi-node jobs onto the cluster. That we can tune the parameters using additional properties to get things like email notification and wall time, and that there are best practices for submitting your jobs, whether it's how we get files transferred over to run your job, how we do error handling with things like getting the schedule ID, getting error messages, getting debug log files, and so forth. And that in the end, if this is something that you feel would be of benefit and value, all of this is readily available, and that you should start with the TÜBİTAK folks to help get you started for your next step. So. And with that, I've concluded my slides. Unless there's any questions, I'm going to hand it back over to Alex.
I see that in the meantime, Truba has posted a useful email address for request of support Okay, so what a ride, Raymond. It's been 2 hours of delivering content. So let me thank you for the content itself and the energy that you have put in presenting. And also once more, let us thank all the organization and people that have allowed us to run this workshop. In premise, TÜBİTAK, that manages the Truba cluster. We had guest presenters from Bilkent University, the Simply Complex Lab. Thanks a lot. And a number of people have been working in the background, addressing questions, answering. Let me mention one for all. Jonathan, thanks a lot for your help and support. The meeting has been recorded, and a copy of the PowerPoint presentation will be made available to the attendees likely next week. We'll have to do a little of edit and changes, but then we will reach you and share locations where you will be able to download the presentations and the recording of the workshop. With this, you have been very patient, following us for more than 2 hours. Thanks a lot. Have a good day.